Welcome to The Explainer. Today, we're diving right into a hyper-analysis of something you probably see all the time, but maybe haven't really thought about. We're looking at a single, everyday culinary process that's actually a masterclass in mechanics and material science. We're talking about culinary extrusion. So, let's figure out how everyday engineering solves a really delicate culinary problem right in the kitchen.
Just look at this visually satisfying, continuous coil of ground meat forming perfectly on the dark plate, resting right there on a bed of green lettuce. If you squint a little at the dark background on the top left, there's actually a faint line of text declaring this an efficient sausage filling machine. And, it's a pretty bold claim, but as we're going to see through this visual deconstruction, they hit the nail right on the head. It's totally accurate.
But before we actually break down the tool itself, think about the core problem here. How in the world do you perfectly pack a super delicate, basically paper-thin casing with really dense ground meat, all without ripping it to shreds? It's kind of like a giant puzzle. You've got heavy, wet material being forced into a fragile membrane that's meant to stretch, sure, but only up to a very strict breaking point. Getting it right requires intense precision, and this little device manages it through an incredibly delicate balancing act. Section 1. The perfect sausage coil. The end result of efficient extrusion.
The physical evidence we're looking at is just striking. That smooth, completely unbroken coil resting on the plate, that doesn't just happen by luck. It is direct proof of incredibly steady, controlled, downward manual pressure from whoever is operating it. If they push down with jerky or uneven movements, you'd instantly get bulging sections, thin weak points, or basically every sausage maker's worst nightmare, a total casing blowout. So the absolute uniformity of that coil proves the downward force perfectly matches what that little casing can actually hold. At its core, what we're witnessing is textbook extrusion. Simply put, that's the process of forcing a material through a die or a nozzle to create a specific, continuous shape. By linking this culinary visual to a mechanical concept we use literally everywhere in manufacturing, it really shifts your perspective. We aren't just looking at cooking anymore. This is basic manufacturing happening right on a kitchen table. The ground meat is our raw material, and that plastic funnel acts as the die, transforming a chaotic mix into a perfectly uniform cylinder. Okay, Section 2, Anatomy of the Stuffer. Let's deconstruct the mechanics. If you visualize this thing in motion, it boils down to a really straightforward three-step process. First, you load the raw ground meat right into that main clear cylinder. Step 2 brings in the human element, applying consistent manual downward pressure from the top. And finally, step 3 is the payoff, where that dense meat is forced to extrude right out of the narrow, tapered nozzle at the bottom. Laying it out like this really helps visualize the flow of energy. You can see exactly how human force gets directly transferred into shaping the food. Taking a visual inventory of the tool itself, you realize every single piece has a highly optimized purpose. You've got the clear primary cylinder, which is brilliant because it lets the user actually monitor meat levels in real time. Even better, they can spot sneaky air pockets before they ruin a whole link. Then there's the thick black locking collar at the base, the tapered extrusion nozzle we just mentioned, and of course, that delicate translucent casing bunched up right at the very end. Now, you might look at that stark black collar and think it's just a sleek design accent, right? But mechanically speaking, it's absolutely crucial. It's the most vital joint on the entire device. When you press down hard on dense meat, you're creating massive outward force. That black collar acts as the heavy-duty anchor, securely locking the clear cylinder and the extrusion nozzle together under all that high pressure. Without that heavy-duty reinforcement, the intense pressure from the compacted meat would literally blast the nozzle right off the end of the tube, and you'd have raw meat flying absolutely everywhere.
Moving on to Section 3, Adapting to the casing. One machine, multiple sizes. Just below the main action, take a look at the array of extra parts resting neatly on that light wooden table. Right beside the plate, you'll see a lineup of 4 separate, stark white funnels. Notice how they dramatically vary in diameter at their tips? Yup, this is absolutely not a one-size-fits-all operation. The whole setup is cleverly designed to give you complete control over the final product's dimensions. And this brings us to the simple genius of the machine's adaptability. Check this out. All 4 of those nozzles have identically wide, flanged bases. That means every single one of them attaches universally to that supercritical black locking collar we were just talking about. But their opposite ends get progressively narrower. So while the base stays universal to lock into the machine, it's the narrow end that actually dictates the specific thickness of your final sausage. It's just an incredibly elegant, efficient engineering solution for swapping out sizes on the fly. So, jumping back up to the active nozzle in the user's hands, look at that translucent casing, heavily scrunched up along the shaft of the funnel. Honestly, this is where the real magic happens. As that thick meat pushes forward out of the tip, it naturally grabs the inside of the casing, gently pulling it forward. So that scrunched casing elegantly unspools off the tube at the exact same rate the meat is extruded. It's a completely self-regulating feed system, driven literally by nothing but the friction of the meat itself. How cool is that?
Ultimately, what all this proves is that you definitely don't need million-dollar complex robotics for perfect manufacturing. A totally straightforward, hand-operated design, combined with the incredibly simple physics of extrusion, yields perfectly uniform, professional-looking culinary results right at home. The clear tube lets you monitor, the secure collar holds the pressure, and the interchangeable nozzles adapt to your needs. They all come together to solve this really specific packing problem perfectly, every single time.
Which leaves us with one final, kind of fascinating thought. We've just seen how flawlessly this simple, hand-powered tool operates. But if manual extrusion is really this effective, how exactly does this simple technology scale up? Think about massive industrial food production factories, pumping out stuff around the world. How do these exact same mechanical principles, the pressure, the extrusion, the unspooling casings, how do they operate when you are processing thousands of pounds an hour, instead of just one plate? It's definitely something to chew on the next time you see a perfectly uniform product lined up at the grocery store. Thanks so much for joining me on this explainer, and we'll catch you next time.